Hi class, in this video we are discussing inference techniques about the difference between two population means for large and independent samples. These are data sets from two groups of population. The techniques that we will focus on here are creating confidence interval for large and independent samples of two groups of data, and testing hypotheses for large and independent samples of two groups of data. In the previous videos and during class, we've discussed creating confidence interval and conducting hypothesis testing for one sample mean. If you still remember, the formula for your confidence interval for one sample mean is x bar, where this is the point estimate plus minus z. We are going to use the normal distribution for large samples and sigma x bar. If you also still remember, z sigma x bar is also called the maximum error, and sigma x bar is called the standard error, and z alpha over 2 is called the critical value. We've also learned about margin of error during estimation, where the formula is plus minus 1.96 multiplied by the standard error. So this is the estimation for one population mean. The hypothesis testing for one population mean, if you still remember, the null hypothesis would be mu equals or greater or equals or less or equals to a value, and the alternative is mu not equals to or greater than or less than a value. Now we are discussing making inferences about the difference between two population means for large and independent samples. When are the sample size of the two population considered large? Because we have two population, I'll name it as population 1 and population 2. And so the sample size would be sample size for population 1, and the sample size for population 2 must be greater or equals to 30 in both cases. So these two conditions must be fulfilled for the sample size to be considered large. And next, we are going to discuss the definition of independent samples. It is when the selection of one group of sample does not affect the selection of the second group of sample. I would prefer to illustrate the term independent and dependent groups with an example. Let's say I would like to conduct a study to investigate the difference in brain activity among patients with COVID-19 and healthy control subjects. Okay, so I have two groups of samples right now. These are considered independent groups. So the selection of the subject in this group does not affect on the selection of subjects in this group. So I'm interested here on the brain activity. Now consider another example where I would like to investigate the effect of medication on brain activity of patients with COVID before taking the medication and after taking the medication. So now here, my subjects in the first group are also the subjects that I'm interested in the second group. So I have similar subjects for the first and the second group. In the independent group, the subjects in the first group is not related to the subjects in the second group. Let's take another example. And now I have female students and male students in my class. Let's say I would like to conduct a study to investigate the difference of their final exam marks. So the first group of subjects would be the female subjects of my class, and the second group of subjects would be the male subjects of my class. These are independent groups. Another case, I'm interested in comparing the marks of a quiz for students before watching this video and after watching this video. These are dependent samples. At this point, you might question the need to study inference when you could get results from your sample data directly by computing the mean. However, scientists are always interested in the results of a population. So the process of inference, which are estimation and hypothesis testing, would generalize the results from your sample data to your population data. And also, we've learned that different samples produce different results. Using the techniques of inference, such as estimation and hypothesis testing, we are able to generalize results with some degree of certainty. This is the role of your alpha. Okay, so we are ready for the formulas that are related to the hypothesis testing of the difference between two population means for large samples. So the mean of the difference between two groups of samples is denoted by mu x bar 1 minus x bar 2, and this is equivalent to mu1 minus mu2. If you still remember, in your sampling distribution, the mean of the sample mean, or mu x bar, is equals to mu. And because we normally do not have the value of the population mean, we would estimate this using the value of the sample mean. So similarly, in hypothesis testing for two population means, we would use the values of x bar to estimate mu. The standard deviation of the difference between two sample means is given as this. Now, if you still remember, sigma x bar is equals to sigma over square root of n. If the value of sigma is unknown, we could estimate using the value of the sample standard deviation. Regardless of the shape of the two populations, when the sample size are large, the shape of the sampling distribution of the difference of the sample means would be approximately normal. So in this case, it would be approximately normal. And the value in the middle here would be mu of x bar 1 minus x bar 2, which is mu1 minus mu2. If you still remember, in the sampling distribution of x bar, the value in the middle here would be mu x bar which is also equals to mu. Alright, so we've discussed the confidence interval for estimating mu, which is x bar plus minus z when the sample size is large, sigma x bar. So the formula for the confidence interval of mu1 minus mu2 would be, instead of x bar, it is now x bar 1 minus x bar 2. And instead of sigma x bar, it is now sigma x bar 1 minus x bar 2. And if we do not know the value of sigma, we estimate using the sample standard deviation. Looking at an example always makes things so much simpler for us. So let's look at an example. To help you get used to answering questions, we will try out this exercise by using the formula provided in your final exam. Okay, let's start. In this example, we have information about the diameter of steel rods by two machines A and B. So we have machine A and machine B. A sample of 50 steel rods is taken from machine A. Okay, so the sample size is 50 from machine A. And they gave an average diameter of 8.56 millimeters. So this would be the sample mean with standard deviation of, okay, so this is the sample standard deviation 0.5916. Another random sample of 35 rods is taken from machine B. So sample size of machine B is 35. An average of 8.78 and standard deviation 0.6325. Question A. Let mu1 and mu2 be the population means of diameter of steel rods produced by machine A and B respectively. What are the point estimate of mu1 minus mu2? Okay, so the point estimate of mu1 minus mu2 would be x bar 1 minus x bar 2. Okay, so machine A, I will rename this as machine 1. And machine B, I will rename this as machine 2. So x bar 1 would be 8.56 minus x bar 2 is 8.78. This gives us negative 0.22. What is the margin of error? Okay, easy. What's the formula for your margin of error? Plus minus 1.96 sigma x bar 1 minus x bar 2. Okay, I'm not sure if you could already remember the formula for sigma x bar 1 and x bar 2. And anyway, we do not have the value of sigma, we only have the value of the sample standard deviation. So instead of sigma, this would be sample standard deviation. I'm going to check the formula of the sample standard deviation of x bar 1 minus x bar 2 in the formula, which is in the appendix of your final exam. So I've already uploaded the file in Ulearn. Please check that one out. So for large samples, the formula for the sample standard deviation of x bar 1 minus x bar 2 is square root of s1 square over n1 plus s2 square over n2. Let's rewrite that. This equals to plus minus 1.96 square root of s1 square over n1 plus s2 square over n2. And this gives us plus minus 1.96 square root of 0.5916 square over 50 plus 0.6325 square over 35, and this is plus minus 0.2661. Okay, on to question B. Construct a 97% confidence interval for mu1 minus mu2. So a 97% confidence interval for mu1 minus mu2 is equals to x bar 1 minus x bar 2 plus minus z, the critical value, and square root of this one here, s1 square over n1 plus s2 square over n2. This formula is also provided in your final exam appendix. I'll show you. It's this one here. So we have 8.56 minus 8.78 plus minus. Okay, let's check the value of the critical. Let's check the value of Z. So 97% will be the area in the middle here. And this is Z alpha over 2. How much is this? 1 minus 0.97 divided by 2, which is 0.015. Let's check the negative value of the Z alpha over 2 in our normal distribution table. Probability is 0.015. It's the one here. It gives us negative 2.17. So Z alpha over 2 will be 2.17. Square root of 0.5916 square over 50 plus 0.6325 square over 35. So our 97% confidence interval of the difference of the two population means are negative 0.5146 to 0.0746. In the hypothesis testing of two population means, the null hypothesis normally says that there is no difference between the two means, or that mu1 is equals to mu2. We could also rewrite this as mu1 minus mu2 equals to 0. Similarly, the equal sign here could also, depending on the question, be greater or equals to or less or equals to. And the alternative hypothesis would normally test that there is a difference between mu1 and mu2, or that mu1 is not equals to mu2. We could also rewrite this as mu1 minus mu2 is not equals to 0. And depending on the question, sometimes we would like to check whether mu1 is less than mu2 or mu1 is greater than mu2. So what we've discussed just now is simplified in the table here. It could be written as this or this, and both are correct. The test statistics for hypothesis testing of the difference the means of two groups for large samples is given as the one here. And if you still remember previously, the hypothesis test for one mean was x bar minus mu over sigma x bar. There is not much difference between these two formula except that your x bar is now x bar 1 minus x bar 2, or the difference of the two sample means, and your mu is now mu 1 minus mu 2, and sigma x bar is sigma x bar 1 minus x bar 2. So this is just an extension of the previous formula. So the value of mu 1 minus mu 2 is substituted from the null hypothesis. Let's look at this example. A math lecturer claims that students in his class will score higher on their midterm than students in another colleague's math class. Definitely, we already know the alternative hypothesis, which is the scores of his students is higher than the scores of his colleagues' students. So mu 1 is greater than mu 2. And because this has no equal sign, it goes to the alternative hypothesis. So you could write it this way, or you could write it in this way. Mu 1 minus mu 2 is greater than 0. I'm going to keep it as this way. So the null hypothesis would be the scores are the same, or it is less or equals to 0. I'll just leave it as equals to 0. Okay, let's extract the values in the paragraph. The mean midterm math score for 50 students in his class. So I will name the groups in his class as 1 and in his colleague's class as 2. 50 students in his class, the sample size is 50. The sample mean is 22.2 and the sample standard deviation is 4.8. The mean midterm math score for 45 of his colleagues' students is 18.8 and the standard deviation is 5.5 and alpha is 0.05. So let's move on to the test statistics. Z star would be x bar 1 minus x bar 2 minus mu 1 minus mu 2, which is equals to 0 from our null hypothesis. This is 0 divided by s x bar 1 minus x bar 2, which is the square root of... So if you can't remember the formula, you could always go and check the formula from your final exam appendix. Yes, we have the test statistics here. Okay. So sigma x bar 1 minus x bar 2 is this one. It's just that we substitute sigma with s1 square over n1 plus s2 square over n2. So s1 square over n1 plus s2 square over n2. This gives us 3.1942. Next is the rejection region. And because the sample size is large, we are definitely using the standard normal distribution. We have a right tail test. Alpha is 0.05. Let's find the critical point. So when alpha is 0.05, the probability towards the left is 0.95. We have these two values, 1.64 and 1.65. You could take either one of these values. So I'm going to take 1.65 as the critical point. 1.65. And what's the next step? Yes, we are comparing the test statistic with the critical point. So this definitely falls somewhere in the rejection region. Let's make a decision and a conclusion. Z star falls in the rejection region. So we reject H null. What happens when we reject H null? mu1 minus mu2 is greater than 0. Can the lecturer's claim be supported? What is the lecturer's claim? I forgot to write it out, right? So, a math lecturer claims that students in his class will score higher. So this is when the lecturer's claim is true. And this is when the lecturer's claim is false. So because we rejected the null hypothesis, then we come to a conclusion that the lecturer's claim is true, or I would write it as the lecturer's claim that students in his class will score higher on their midterm than the students in his colleague's class is supported. Okay class, that's all I have for the hypothesis testing of two population means. I hope I've made it easy for you to understand the concepts, and I'll see you in the next lecture video.